All right, so in our previous video, we talked about this chapter question, and you'll see this chapter question appear on your test. So kind of to revisit, we want to figure out ways in which we can make this primary and secondary amine alcohol and this ether. So far, you've definitely learned that you can use reduction reactions. And so we can reduce carbonyls, but you want to know what kind of carbonyl. We can use Grignard reactions, but what kind of carbonyl do we need with the Grignard for both of these two types of reactions? So you're going to need different kinds of carbonyls for each. In Organic 1, you learned substitution reactions, and so we can do a substitution to make an ether, and we'll talk about this a little bit more with the Williamson ether synthesis. And so you want to spend some time figuring out how each one of these work. So again, we're going to be continuing on with our reactions. And so we wrapped up last time, our last video, talking about LAH being another way that we can reduce ketones and aldehydes, but they're so reactive, they're unnecessary. We do use them, however, for milder reagents like esters. And I'll talk about what that mechanism is with esters. And with esters, it actually reacts 2 times. So that kind of tells you there's something a little bit different about our mechanism. And we're going to go into that right now. So this mechanism, the generic mechanism, is called, it's very similar to our last one, which was an acyl nucleophilic addition, but this one is an acyl nucleophilic substitution. It starts out with first the acyl nucleophilic addition. So it's an addition reaction, kind of like what you learned in the electrophilic additions, but then it moves into a substitution, kind of like it's similar to an SN2. Now it's like an SN2, but it's a reaction that happens on itself rather than multiple reactions, and then it will give us our final product. So the generic idea is that you have your ester, or there's some other carboxylic acid derivatives. It just cannot be carbon here or hydrogen. If it's a carbon or a hydrogen, this is going to be a ketone or an aldehyde. So we take our nucleophile, and we need a stronger nucleophile to carry out this entire mechanism. So this first step is actually, it's harder because this is a milder electrophile. It's harder to react, so we need a stronger nucleophile than sodium borohydride. And so that's why we use lithium aluminum hydride. But just like our previous mechanism, again, it's the same acyl nucleophilic addition. You attack the carbonyl carbon and you open that pi bond. But this is where something interesting happens before we can even just protonate. So before you can run to the hood, get your acid, do your protonation, before that even happens, there's no acid here. That this, even though it's mild, it's a mild leaving group. And this molecule is very unstable the way it is. It doesn't like being that way, so it prefers to have back that pi bond. So what it does is it kicks out the leaving group. And so that's why I said this could be other things. It's just some sort of mild leaving group. It kicks it out, and that hydrogen's still there because we just added this hydrogen from our nucleophile, and we just kicked out that leaving group. Okay, so this was our original leaving group. All right. Now, we have lithium aluminum hydride, so just because I showed the mechanism with one doesn't mean there's only one. There's a lot of them in there, right? And it can't help itself. It sees an electrophile, and it happens to be an even stronger electrophile than what we had. So this reaction is just not going to stop. So this is immediately going to react. And now we added a second hydrogen. Now I have no more leaving groups. So this is just going to sit here and not do anything. So now we've gotten an alkoxide that's just going to stay there and not do anything until you protonate it. So now once you've gotten the acid, so this is going to be no more reaction. You're going to use your acid, H3O plus, and we're going to remove one of these hydrogens, and we get an alcohol. So whenever you see these leaving groups like your ester, the thing to remember is that you're going to add a hydrogen here, and you're going to add a hydrogen, and you're going to replace this with a hydrogen. So you're essentially going to take this and you're going to make a primary alcohol. So this is another way of making a primary alcohol, and it's because you're reacting it 2 times. So before we move on, I'm just going to draw a generic acyl nucleophilic substitution, because I can do this with any nucleophile. And so I'm just going to use leaving group because in our next chapter we're going to see that this leaving group could be other things. All right, so there are many other leaving groups that we can use, and they're going to just behave differently. They're going to change the electrophilicity here. So you have a generic nucleophile. It attacks the carbonyl carbon, opens the pi bond. Because I have this leaving group, it's going to do something very similar to the SN2. So remember, I said this is kind of like an SN2. So this comes down, this acts like a nucleophile kicking off a leaving group. So it's like SN2 like. Okay, so this, you can treat the lone pairs as like a nucleophile kicking out a leaving group. We end up with a carbonyl again, which then can become reactive, and another nucleophile can come in and attack. And so we basically are just adding 2 of our nucleophiles. As long as this nucleophile can't come back off, right? So we're going to say that it's a poor or very bad leaving group that you've just added. As long as it's very bad and hard to come off, my next step is protonation. So it should be pointed at the hydrogen. And you get your alcohol. And so we can use different nucleophiles. So we'll talk about this later. We can use a Grignard, for instance, as a nucleophile, etc. So from your reading, from your textbook, you should be able to answer this question. And this is also a review from Organic 1. All right, also from your reading, and this is if you pay close attention to what it says here, as well as anything that I just mentioned a little while ago, you should be able to answer this question. So let's talk about these reactions that I mentioned. We just talked about these mechanisms from last time and this time. One thing that we have to keep in mind, just like when we learned about addition reactions onto a carbon-carbon double bond, very similar thing you have to keep in mind. This carbon is trigonoplanar. So in regards to stereochemistry, when your nucleophile attacks, because this electrophile is planar, the nucleophile is going to attack from either face. So either the top face or the bottom face, which would mean for us that we're going to get a mixture of products. In theory, so theoretically, if your molecule is chiral, you should end up with a racemic mixture. That's only if it's chiral. You can't get racemic mixtures for things that are not chiral. So in terms of the stereochemistry, you would end up with mixtures because you're adding across something that is flat. Now in terms of regiochemistry, and we'll talk about this more later, this is not something I want you to focus on, but I want you to take notes because this will come back up again, is that ketones are less reactive than aldehydes, especially as we increase sterics. Okay, we'll talk about in the next unit why that is, but ketones are less reactive than aldehydes, and ketones and aldehydes are way more reactive than carboxylic acids, esters, etc. So we'll talk more about that, why the reactivity of ketones and aldehydes in the next unit, but we will talk about the differences in carboxylic acids and esters, etc. another time. Now, what does that mean? Well, if you're talking about how fast something will react, aldehydes will react faster than ketones. And when we say we have some sort of leaving group on here, those are your carboxylic acid derivatives. Ketones and aldehydes are faster than those. And so if I ask you about the rate of the reaction, you can tell me that, the speed, which one's faster or slower. You could also say if I had two functional groups on the molecule. So for instance, if I had ester versus a ketone, you know that a ketone would be faster. If I used LAH, that's one. The second thing is, that LAH will react with both ketones and esters, and so both of them would react. But if I use sodium borohydride will only react with the ketone because the ketone is weaker, so is stronger than the ester, so the ester won't react. So no reaction with the sodium borohydride. Okay, and so in terms of stereochemistry, we can talk about the place in which these reactions can happen by either a weaker or stronger nucleophile or how fast each electrophile can react. And so here we're going to go back to this mechanism again. So if I had a carboxylic acid or had an ester, and there's some other reactions that we have, we can make them into primary alcohols. So sodium borohydride will not do that. So in terms of regiochemistry, you won't see sodium borohydride do that. One thing your textbook doesn't tell you, and I want to say this, actually it's even better that instead of LAH, we use BH3 for this. That works even better. So just take a note of that. So as I talked about a little bit, is that we could use LAH and it will react with all the carbonyls. I can use sodium borohydride and it favors ketones and aldehydes. This is what we call tuning the reagent. So we can actually fine tune the reagent so it only reacts with certain things. Why that is the case for some of these things, you don't have to know quite right now. Some of them will start popping up as we get to them. But one of the reasons that we know that this works really well is that I can change different groups on my nucleophile, like lithium aluminum hydride and sodium borohydride. Instead of all hydrogens, I can change these to different groups. So I can, for instance, make these into alkoxides, and I find, not me because I didn't personally discover this, but people have found that that makes it so that it reacts with certain types of carboxylic acid derivatives better than others. People have also found that by having sterically bulky groups in these positions, I can favor certain types of molecules over the others. So even though they react, all with ketones, they may be reacting with different kinds of ketones differently. So I can fine tune my reactivity. That's one. And remember, I said that you are not going to get one product, you're going to get a mixture of products if your molecule ends up being chiral. Well, one thing people can fine tune is that they can change the R groups into something chiral, or they can add some sort of auxiliary. So when I say auxiliary, auxiliary means a helper to the agent to make it behave chiral. Why is that important? So, for instance, if I took lithium aluminum hydride and I change whatever group here into something that's chiral, it's going to force that uh, sodium borohydride derivative to only react on a certain parts of the molecule more than the other, because it's going to be easier to get to one part of the molecule probably than the other. So people have done various experiments. There's not an easy set way that I can give you an answer to which side or how. A lot of that's experimental. But I want to point out that that's what people do. So for instance, in the lab, one experiment that I've often done in the past with students is I've taken sodium borohydride and reacted that with a salt that you learned about in Organic One, tartaric acid, which has some chirality to it. You mix them together, they associate with each other, and they produce a reducing agent that only reacts primarily on one side of your carbonyl. The other thing that we've seen is that people have used enzymes that have certain chirality that only reacts on one side. So enzymes are another example. So for instance, there's an enzyme in carrots that do the same thing where they only react on one side of the ketone or the other. So let's